Welcome back to Basic Electronics. In the last lecture, we got started with a series RC circuit with a periodic piecewise constant input, namely a square wave. We will now continue with that example and work out the steady state solution. We will also learn about the meaning of charge conservation for a capacitor and look at its implications for this specific example. So let us begin. In order to find these constants A and B, we need two conditions on Vc in phase 1. Condition number 1, at t equal to 0, this time point here, Vc is equal to V1. What about condition number 2? Let us look at this interval. In this interval, the input voltage Vs is equal to V0 and the capacitor has started charging. Now in this phase, the circuit is not aware that this transition is going to take place, and therefore its response would be as if this voltage did not change. And if that were the case, then this Vc would finally reach V0 as t tends to infinity. So Vc at t equal to infinity is equal to V0, and that gives us the second condition on Vc. So these are the two conditions we have. At t equal to 0, Vc is V1, and at t equal to infinity, Vc is V0. Now using these conditions, we can find A and B. B turns out to be V0 and A turns out to be V1 minus V0. So putting these back in this equation, we get Vc in phase 1 equal to minus V0 minus V1 times e raised to minus t by tau plus V0. Note that this number is positive because V0 is larger than V1. Alright, now let us look at the T2 phase and let Vc in the T2 phase, denoted by this superscript 2 over here, be A prime e raised to minus t by tau plus B prime. To find these constants A prime and B prime, we need two conditions on Vc in phase 2. One of the conditions is that at t equal to t1, Vc is equal to V2, and the second condition is that as t tends to infinity, this Vc would have gone to 0. Alright, so these are the two conditions that we can use, and with these conditions we get B prime equal to 0 and A prime equal to V2 e raised to t1 by tau. And when you substitute these back into this equation, then we get Vc in the T2 phase equal to V2 e raised to minus t1 by tau. Alright, so these are the two equations that describe Vc of t. The first equation describes Vc in this interval, and the second equation describes Vc in this interval. And notice that our job is not done yet because we have these unknowns V1 and V2 here, and we need to figure them out. And to find V1 and V2, we can use these conditions here. What do they say? Vc in phase 1 at t equal to t1 is equal to V2. This is Vc in phase 1, and at t equal to t1, that is this time point here, we have Vc equal to V2. So that is the first condition over here. Second condition, Vc in the T2 phase at t1 plus t2 is equal to V1. This is our Vc in the T2 phase, and t1 plus t2 is this point here. So what this equation says is that this Vc at t equal to t1 plus t2 is equal to V1. The first condition here gives us this equation 3. Let us see how. What is this condition? It says that Vc in the T1 phase at t equal to t1 should be equal to V2. What is Vc in the T1 phase? That is given by this equation 1 here. So we substitute V2 over here and we substitute t equal to t1. and that gives us this equation. It is V2 equal to minus V0 minus V1 times e raised to minus T1 by tau plus V0. The second condition, namely Vc in the T2 phase at T1 plus T2 equal to V1, gives us this equation here. Let us see how. What is Vc in the T2 phase? That is given by equation 2 here. So what we do is substitute V1 over here, and for T we put T1 plus T2, and then we get V1 equal to V2 e raised to minus T1 plus T2 minus T1, the whole thing divided by tau. This T1 cancels out, and then we get V1 equal to V2 e raised to minus T2 by tau. To simplify the algebra, let us define two quantities, A equal to e raised to minus T1 by tau and B equal to e raised to minus T2 by tau. And using these A and B, we can rewrite equations 3 and 4 as follows. Equation 3 can be written as V2 equal to minus V0 minus V1 times e raised to minus T1 by tau. Now this quantity is the same as A, so therefore A comes here, plus V0. And equation 4 can be rewritten as this one here. V1 is equal to V2 times e raised to minus T2 by tau, and this quantity is defined as B. So therefore we have V1 equal to B times V2. And now we can solve equations 5 and 6 to obtain V1 and V2. And the results are written over here. Okay. Now if we know R and C, we can calculate tau. Tau is equal to R times C. And if we know T1 and T2, then A and B can be calculated. So therefore this entire factor is known. And if we know V0, that is the maximum value of the input voltage, then V1 and V2 can be computed. Once we know V1 and V2, we have the complete picture for Vc in the T1 phase and Vc in the T2 phase. Here the results are summarized for the capacitor voltage. We have V1 and V2 here in terms of A and B, where A and B are given over here. And once we know V1 and V2, we can find Vc in the T1 phase using this expression and Vc in the T2 phase using this expression. Alright. Let us now look at the current calculation, IC of T. And once again, this will have two parts, IC in the T1 phase and IC in the T2 phase. How do we go about this? There are two ways of obtaining the current. One, we already know the capacitor voltage in the T1 phase as well as in the T2 phase. All we need to do is to differentiate that, multiply that by C, and then we get IC of T. Now this is something that you must do as homework. We will not do that here. The second method is to start from scratch. Pretend that we don't have these results and we start from the beginning and see what we get. And in doing that, we will definitely learn something more. Okay, let us proceed further. Oh, the stop sign has come now. What is it saying? It is saying that there is something to be completed, and that is this homework over here. So you really should stop the video at this point. Compute IC in the T1 phase and also in the T2 phase by differentiating the capacitor voltage in the T1 phase and in the T2 phase. And once you are done with that, you can get back to the video. Let us begin with IC in the T1 phase, this part, and let IC be A e raised to minus T by tau plus B, and that is IC in the T1 phase, and that is denoted by this superscript 1 over here. Our job is to find A and B, and for that we need two conditions on the capacitor current. One condition is obvious. At t equal to 0 we have IC equal to I1. What about the second condition? The second condition comes from the fact that if this change did not happen, that means if this input voltage continued to be V0, then this IC would have gone eventually to 0. So that gives us the second condition, namely IC at infinity equal to 0. So these are the two conditions we can use to find A and B. So B turns out to be 0 and A turns out to be I1, and putting this back in this equation now, we get IC in the T1 phase equal to I1 e raised to minus t by tau. Alright, let us now look at the T2 phase. That means this part of IC of t. And in that phase, let IC be A prime e raised to minus t by tau plus B prime. And here we put a superscript 2 to denote that we are in the T2 phase. Now to find A prime and B prime, we need two conditions on IC in the T2 phase. The first condition is that IC at t equal to T1 is equal to minus I2. What about the second condition? The second condition can be obtained using the fact that this current would have gone to 0 at t equal to infinity if this change had not happened. So these are the two conditions that we can use, namely IC at T1 equal to minus I2 and IC at infinity equal to 0. And with these conditions we get B prime equal to 0 and A prime equal to minus I2 e raised to T1 by tau. And putting these back in this equation now, we get IC in the T2 phase equal to minus I2 times e raised to minus t minus T1 divided by tau. Our next step is to find these unknowns I1 and I2 in equations 1 and 2, and let us see how to do that. Let us look at this picture. This is our IC in the T1 phase and that is our IC in the T2 phase. At t equal to T1, IC in the T1 phase is this value here, and at the same time IC in the T2 phase is this value over here, which is minus I2, and the difference between these two is denoted by delta over here. So let us first figure out what this delta should be. At this point t equal to T1, the input voltage is changing from V0 to 0. The capacitor voltage is not really changing because Vc at T1 minus is the same as Vc at T1 plus, and therefore coming to this circuit now, we observe that there is a change in Vs, there is no change in Vc, and therefore this change in Vs must appear across this resistance, otherwise KVL would not get satisfied. Vs is changing by V0, this quantity here, and therefore the voltage across the resistor must also change by V0. And what does that mean? That means there must be a corresponding change in the current IC here, which is V0 divided by R, and therefore we conclude that this delta must be equal to V0 by R, and that is what we write over here. IC in phase 1 at T1, that is this value here, minus IC in phase 2 at T1, this value over here, must be equal to V0 divided by R. And by the same logic, this difference must also be V0 by R. Now what is this value? This IC value is the same as this IC value, and that is IC in the T1 phase at t equal to 0. What about this value? That is IC in the T2 phase at t equal to T1 plus T2, and the difference between these two values must be equal to V0 by R, and that is what this equation says over here. The rest is straightforward. What is IC in the T1 phase at t equal to T1? This is our equation for IC in the T1 phase. So let us put t equal to T1 over here, and then we get this first term over here. What about IC in the T2 phase at t equal to T1? This is our IC in the T2 phase. So we put t equal to T1 here. Then we get e raised to 0, that is 1. And therefore, this IC at T1 boils down to minus I2, like that. And the difference between these two terms must be equal to delta. Let us use this second condition now. What is IC in the T1 phase at t equal to 0? We put t equal to 0 here, and that gives us I1, the first term here. What about IC in the T2 phase at T1 plus T2? We put t equal to T1 plus T2 over here, and then we obtain this expression over here. And the difference between these two must be equal to delta. Note that T1 cancels out over here, and we get e raised to minus T2 by tau. Now, using the constants a and b that we defined in the previous slide, we can rewrite these equations 3 and 4 as a I1 plus I2 equal to delta, that is our equation 3, and I1 plus b times I2 equal to delta, that is our equation 4. And these two equations can now be solved for I1 and I2. I1 turns out to be this expression here, delta times 1 minus b by 1 minus ab, and I2 is delta times 1 minus a by 1 minus ab, where a is e raised to minus T1 by tau and b is e raised to minus T2 by tau, as we saw in the last slide. So now we have obtained expressions for the capacitor voltage Vc in the steady state, both in the T1 and T2 phases, and also we have got expressions for the capacitor current Ic in the T1 phase as well as in the T2 phase. But let us go a little bit beyond that and look at the implications of charge conservation, and in the process we will learn a lot more about these waveforms. Here is a schematic diagram showing a capacitor. There is one metal plate over here with charge plus Q, and there is another metal plate here with a charge minus Q. If this is plus Q, this has to be always minus Q. These two metal plates are separated by a dielectric with a thickness T and a dielectric constant epsilon. Now in real life, these may not be quite plates, these may be metal foils, and the insulator may also be in the form of a dielectric film, and this whole thing may be rolled in a cylindrical shape, for example. In any case, the cross section does look like this, and the capacitance is given by epsilon A by T, where epsilon is the dielectric constant of this insulator and T is the thickness. A here is the area of the capacitor. Alright, let us now look at the charge here, plus Q on this plate and minus Q on this plate. This charge can change only if there is a non-zero current IC, either entering this terminal or leaving this terminal. And the relationship between IC and Q is given by IC equal to dQ dt. And since Q is C times Vc, we get IC equal to C times dVc dt. And this of course is the equation that we have been using all along. Let us now look at the implications of this equation in our context, and in particular we will look at the implications in the periodic steady state. What is the meaning of periodic steady state? All quantities are periodic, that is x at t0 plus t must be equal to x at t0, where x could be a current or a voltage or even the charge on the capacitor. Let us take x equal to q, the capacitor charge, and then we have q at t0 plus t equal to q at t0. This t is the period. In our case it is t1 plus t2. Alright. Now since IC is dq dt, we can write q as integral IC dt, and let us see what this implies. Now this equation can be rewritten as q at t0 plus t minus q at t0 equal to 0. And because we have this relationship between q and IC, this equation here can be rewritten as integral IC dt from t0 to t0 plus t equal to 0. Let us take a specific case. Let us take t0 equal to 0, this time point here, and then this becomes integral IC dt from 0 to t equal to 0. And now we can split this into two integrals, one from 0 to t1 and the other from t1 to t1 plus t2. So we can write integral IC dt from 0 to t1 plus integral IC dt from t1 to t1 plus t2 equal to 0. And this equation tells us that integral IC dt from t1 to t1 plus t2 must be negative of integral IC dt from 0 to t1. Now let us see what this implies in terms of our graph here. What is integral IC dt? It is simply the area under the IC curve. So this term here, the integral from t1 to t1 plus t2, is this area here, and this is a negative area because our IC is negative in this region. And this integral from 0 to t1 is this area, and that area of course is positive because IC is positive. So what this equation is saying is that these two areas must be equal in magnitude. Let us look at some simulation results now. In particular, let us take t1 equal to t2, 1.5 milliseconds each, R equal to 1K, C equal to 1 microfarad, and V0 equal to 10 volts. With these numbers, using the formulas that we derived earlier, V1 turns out to be 1.8 volts, V2 is 8.2 volts, I1 is 8.2 milliamps, and I2 is also 8.2 milliamps. So our current, the capacitor current, is going to vary between plus 8.2 milliamps and minus 8.2 milliamps. The simulation results are shown in these plots. This is our input voltage, that is the capacitor voltage, and that is the capacitor current in milliamps. Now Vc is going from 1.8 volts to 8.2 volts, and that agrees with these results here. And I1 goes from plus 8.2 milliamps to minus 8.2 milliamps. What about delta, this discontinuity? If you recall, that is expected to be V0 divided by R, where V0 is this voltage, 10 volts, and R is 1K. So delta should be 10 volts by 1K or 10 milliamps. And this is indeed 10 milliamps, the same height as this height here. And this is also equal to delta, that is 10 milliamps. So all is well, and our analysis seems to be correct. Let us now look at the implications of charge conservation. If you recall, we expect the area under the IC curve in the T1 phase and in the T2 phase to be equal in magnitude, and that does seem to be the case. This area is equal to this area here. Here is our second case. What we have done is we have kept T1 plus T2 the same, that is 3 milliseconds, but we have decreased T1 and increased T2. This is our T1, it is now 1 millisecond. This is our T2, it is now 2 milliseconds. With these changes, we get V1, V2, I1, I2 as given by these numbers here, and you can check whether these numbers do actually correspond to the plots which have been obtained by simulation. What about charge conservation? We expect this area to be equal to this area here in magnitude, and that does appear to be the case. This is the third case we have. Once again, we have kept T1 plus T2 equal to 3 milliseconds. We have increased T1 to 2 milliseconds and decreased T2 to 1 millisecond. So this is our T1, 2 milliseconds, and this is our T2, 1 millisecond. And these are the results obtained using our formulas. And you should check that these do agree with the simulation results given here. What about charge conservation? This area is expected to be equal in magnitude to this area, and that does appear to be the case. So there is really quite a lot we can learn from this simple example. Here is the SQL circuit file, and you are strongly encouraged to run this simulation. Make sure that you do get these results that we have shown here. And apart from that, you can make up your own problem, choose some different values of R, C, T1, T2, calculate V1, V2, I1, I2 using our expressions, and then run the simulation to make sure that your values are correct. And in fact, you don't need to stop at simulation. You can go to your electronics lab, hook up this circuit, and verify that the results that you get on your oscilloscope do agree with your calculations. And in that process, you will learn how to use a function generator to generate a square wave with different duty cycles. You will learn how to pick components such as 1K resistor or 1 microfarad capacitor, and you will also learn how to use an oscilloscope. So take this as a learning opportunity, and it's unlikely that you will regret it. Let's consider one more case before we leave this example, and that is T1 equal to 1 millisecond, T2 equal to 2 milliseconds, and we have seen this case in the last slide. But what is different now is the value of R. It was 1K earlier, and now it is 0.1K. And as a result, the time constant, which was 1 millisecond in our previous example, is now 0.1K times 1 microfarad, which is 0.1 millisecond. And therefore 5 tau is 0.5 millisecond, and that turns out to be smaller than T1 or T2. And what does it mean? That means we expect the capacitor voltage to reach its final destination, 10 volts here or 0 volts here. And in fact, we don't even need to use the formulas that we have derived earlier, because we know that the capacitor is going to get charged all the way to 10 volts during the T1 phase, and we know that it's going to discharge all the way to 0 volts in the T2 phase. What about the current? The jump in the current, which we have called delta, is now different because although V0 is the same as 10, R has changed. So the new delta would be 10 divided by 0.1K or 100 milliamps, and that is what we see over here. So the jump here or there is 100 milliamps, and as in the voltage waveform, we observe that the current also does manage to reach its final destination, that is 0 ampere, both in the T1 phase as well as in the T2 phase. That brings us to the end of RC circuits with a piecewise constant source. We will find this background very useful in understanding some of the applications. to be covered later in this course. See you next time.